All right, let's get this started. So yeah, so this week went over motion in 2 dimensions. We went over also motion like circular motion. So if you're in the 9 to 10, or sorry, the 8 to 9 class, most of the stuff is not going to look familiar to you guys because you guys are just starting to go over like velocity and acceleration, all that stuff. So you're going to come upon it soon, probably within the next week or so. So pay attention if you want to study ahead. This is good for you. If not, then focus on last week's worksheet. I'm going to try to go a little quicker this time. Last time was like a 40-minute video or a 15-minute video, and that was way too long. So let's just jump right into it. If you have any questions, comment on the video, and I'll get back to them as soon as I can. All right, so number 1, a ball rolls horizontally off a cliff at a speed of 30 meters per second. It takes about 7 seconds for the ball to hit the ground. Calculate the height of the cliff and the horizontal distance traveled by the ball. Okay, so it's pretty good to do diagrams, pretty helpful. So I'm gonna draw a little diagram. What's going on? We have a ball falling off a cliff. Okay, so ball rolls horizontally off a cliff. Okay, so it's some sort of projectile motion, just like that. Okay, so it's rolling horizontally, so it's going to have some sort of let's see, so it actually gives us the velocity in the x direction, which is so the velocity in the x direction is 30 meters per second because it says rolling off a cliff, 30 meters per second. What else does it give us? It gives us the time. That's good. So again, write down your givens. You're given the time. So it takes 7 seconds for the ball to hit the ground after it falls off the cliff. Okay. And what else is it given? Well, always given is acceleration, right? But acceleration in the y direction in this case. So again, we're starting to break it down to the x and y components. So this velocity is in the x direction. Okay, so we're only given velocity in the x direction. Well, yeah, we'll get to that. So the acceleration in the y direction is gravity, negative 9.8 meters per second squared. Okay, the velocity in the x direction is 30, and then it says it's just rolling horizontally. So all of the 30 meters per second is just horizontal, so the x direction. So we're going to have an initial velocity in the y direction of 0 meters per second. Okay, so it's essentially you're just dropping a ball in the y direction. In the x direction, it's going 30 meters per second. But the y direction starts at 0. So essentially, so I'll just draw it. So y equals 0. So you can visualize it a little better that way. Okay. Acceleration in the x direction equals 0. We don't have an acceleration in the x direction. Okay. Cool. So what do we want to find? Well, we want to find how high the cliff is. So the height of the cliff, and then we want to see how far the ball went, right? So let's say that's h, and the x, or we'll just say this is h, and then we want to find, let's just say this is r, right? Let's say that variable r, which is distance in the x direction. Okay. So again, this is the y direction, this is the x direction. Okay. So let's start off. Which one do I want to do? Let's start off with finding how high it is, right? So let's see how high it is. So what equation am I going to use? Well, a good equation to use here is delta x equals v naught times time plus 1/2 acceleration times time squared. Okay, because we have all these, we have time, we have acceleration, we have the initial velocity. All that we don't have is the change in position, right? So in this case, we're talking about, this is for the y direction, right? So we're trying to find here how high it is. So we're trying to find the height of it. Okay, so now we have to plug in all the variables that we know for the y. Okay, so what is the change in x? Okay, so we're trying to find the change in x, which is the height. Okay, so I'll erase that and change the variable to be height. Trying to find the height. Okay. And then the initial velocity is 0. The time it takes is 7 seconds to hit the ground, plus 1/2, and then we know that the acceleration is negative 9.8 meters per second. Time is 7 squared, right? 7 seconds squared. Okay, and then when you solve this out, you get a height that equals 200, so negative 240.1 meters. So it's negative because the ball is falling in the negative direction, right? So just make sure you understand that. The ball is falling in the negative direction, so you have a negative displacement. So essentially it fell 240.1 meters. All right, so that's going to give you a negative displacement. So just understand that the height of it is positive 240.1. Right, so we'll just say this is essentially the displacement, and the height equals 240.1 meters. Okay, so just understand the distinction there. Yeah, and then when we're talking about the x direction, so how far to go in the x direction, right? So we're trying to find r. So in this case, what do we know? What variables do we know? We know the initial velocity. We know the time it takes. We know acceleration is 0. It doesn't have any acceleration. So we can use the same equation. So we can use this delta x equals v0 time plus 1/2 acceleration times squared. Okay. So if you plug in our variables that we have, I'm going to change delta x into r because that's the variable I'm solving for. And then v0 in the x direction, so the initial velocity in the x direction is 30 meters per second, or I'll just write 30. I leave out the units just because it takes up a lot of room to write the units. 7, but it's good to write the units, you know, just because like canceling out the units, it'll help you out sometimes. Okay, so this whole side of the equation is going to be 0. Sorry, that was supposed to be 7 seconds right here. That's going to be 0, right? 0 times anything is 0. And then 30 times 7. So our distance here is 210 meters. Okay. So our height is 240 meters. The distance is 210 meters. And that's how you solve it, right? So just break it down to its components, into its x and its y. And then you will be able to solve the problem. All right. So number 2. We got 2 identical rocks are thrown off of a building at the same time. First rock is thrown straight downward at 5 meters per second. The second is thrown downward and outward, so that the angle between the initial velocity of the rock and the horizon is 30 degrees. And it's thrown with twice the speed as the first rock. Okay, so which rock hits the ground first? Let's draw our diagram. Okay, so good diagram here, off to the side. We got 2 rocks. Let's say this is rock 1, this is rock 2. Okay, so they're thrown at the same time. They're thrown at the same time. Okay, one is just essentially dropped, or it's not dropped, it's thrown straight downward. Thrown straight downward at 5 meters per second, right? Thrown straight downward 5 meters per second. The other one is thrown at an angle, right? So it's thrown at twice the velocity, but it's at an angle of 30, it's 30 degrees to the horizon. So this is the horizon, right? 30 degrees, it's thrown essentially just like that, okay? At 10 meters per second. Okay, so that's the projectile sort of direction. Okay, so we want to see which rock hits the ground first. Okay, cool. So we know, so first thing I want to do is I want to find out how fast this second rock right here is going in the y direction, okay? And I want to sort of compare it to the first rock, and that'll help me find my answer here, since the force of gravity is acting on them the same. And really the x direction doesn't really matter, like how fast you threw it in the x direction. The only thing that I'm really worried about is how fast it's going in the y direction, because there's no forces acting on it in the x direction. The only force acting on this object is gravity, which is pulling it to the ground, which is, yeah. Okay, so let's dissect this. So just to blow it up over here, we got a rock, right? It's thrown downward at 10 meters per second, okay? Again, horizontal, 30. 30 degrees from the horizon, okay? So we want to find essentially the velocity in the y direction, right? Okay. So we want to break it down into its components, find the velocity in the y direction. Okay, we have the velocity in sort of like the hypotenuse, right? The diagonal direction. We want to break it down now. Okay. So I can easily take this line right here that I drew and draw it over here, and boom, we form that little triangle with a right angle right here, which is perfect, right? I can do my whole sine functions, cosine functions, and I can find whatever this variable is, the velocity in the y direction is over there. Okay, so to do this, I'm going to do sine of this angle. So it's right here. So sine of 30 equals sine of 30 equals whatever the velocity in the y direction is over 10, right? So what we get here is a velocity of y of 5 meters per second when you solve it out. Okay, so this right here is 5 meters per second. It's going in the y direction at 5 meters per second. Okay, so when we break it down into its components, we see that both the velocity of the first rock and the second rock are going in the y direction at the same speed, right at the same instant, right? Even though we threw the rock 2 times harder than the first rock, right? We threw the second rock 2 times harder than the first rock. We threw it in a diagonal, so some of that speed is in the x direction, some of that speed is in the y direction. And it turns out that 5 meters per second is in the y direction. Okay, so then let's think about it. Which one's going to hit first? If we throw them down, straight downward at the same speed, well, they're both being acted on by gravity at negative 9.8 meters per second. So whatever, I didn't give you a distance, but whatever distance it is, it's going to hit the ground at the same time. So it's kind of like a trick question here. Which rock hits the ground first? Well, they hit the ground at the same time. And if you want to calculate it, you can use, you can use whatever equation, delta x equals v naught times time plus 1/2 acceleration times time squared, right? Acceleration is the same. Well, we don't have time, so you probably won't use that equation. But you can use one of the other equations that doesn't have time in it. The accelerations are the same, and the velocities are the same. All the variables are the same, so they're going to hit the ground at the same time, right? So I wouldn't use that equation because of time. So yeah, so they hit the ground at the same time. So it's all about just dissecting it into the x and y variables, and that will give you your answers. All right, number 3. So a ball is kicked off the ground, reaching a maximum height of 60 meters, lands 80 meters away. Calculate the initial speed and the angle above the horizon of the ball when it was kicked. Okay, so let's draw our diagram here. Draw a diagram. Okay, so we got our ball. Ball's being kicked. Goes in a parabolic motion. The height is 60, right? That's how high it goes, 60 meters. And it goes 80 meters. 80 meters. Okay, So what we want to find is this velocity right here. Okay, the velocity in the diagonal direction, and we also want to find the angle at which it's kicked. Okay, so how do we find that velocity? Well, again, breaking it down into its components, maybe we can find the velocity in the y direction and the velocity in the x direction. And then we can use our tan, sine, cosine rules to find that, right? So let's try to do that. Let's try to find the velocity in the y direction, right? So we want to find the velocity in the y direction. What are we given first? We're given in the y direction, we're given distance, right? So how high it went, so displacement in the y. Oh, let's do the vectors now. Okay, so let's say this is the y direction, is 60, cool, 50 meters. The acceleration, we know, is always in the y direction, negative 9.8 meters per second squared. We don't know the initial velocity, and depending on how we define, well, actually, depending on how we define it, we might know the initial velocity. So, or the final velocity. So let's think about this, right? So let's say we start with some initial velocity to kick the ball up in the air, okay? And then it reaches the top point at 60 meters, okay? We have to have some initial velocity to do that. We don't know what that is, but we know the final velocity when it reaches that high point is going to be what? It's going to be 0 meters per second, okay? We don't know the initial velocity, and then obviously, actually, that's what we're trying to find, right? Okay. So let's do that. We have all the variables that we need. We can use, what equation can we use? We can use v squared equals v naught squared plus 2 times negative 9.8 times, so the final position will be 60, and then the initial position will be at 0. That's how we define it. Okay. Okay, and then so we know that what the final velocity is. It's going to be 0, right? Okay. So that's the v squared equals v naught plus 2 times acceleration times displacement. That's that equation right there. Okay. So when we solve, what we're going to do is we're going to bring that velocity over, initial velocity, so it's negative now, equals, I don't want to do this calculation, negative 1176, right? Okay, so when we solve for all this up here, 2 times negative 9.8, we're going to get that. Bring the negative over, v naught equal, or squared equals 1176, and then square root, right? Then we get our velocity initial in the y direction to be 34.29 meters per second. Cool, so we got our velocity in the y direction, okay? So again, breaking this down into its components, we have our ball right here. The velocity in the y direction is 34.29 meters per second. Okay, velocity in the y direction. So this is, again, Vy. We want to find now what Vx is. And then we can find our, we can find that thing, right? The diagonal velocity. Okay, so what do we need to do now? So velocity in the x direction. So velocity in the x direction. The problem with this is, let me look at my notes real quick. So we don't have time, right? We weren't given time. So we actually need time to solve the velocity in the x direction in this case. Okay, so we have an acceleration of 0. because if we were just to plug in, hold on, let me pause this real quick. All right, sorry, my notes were a little mixed up here. So we need time, okay? We need to find time because our acceleration is 0. And if we were to use like this straight up, this equation we used for the y direction, then it wouldn't work out too well because if you plug in 0 there, then our displacement goes away, right? So yeah, it just doesn't work out. Then our velocity initial would be like 0 or equal to 0, and it just wouldn't work out. So we need to find the time. So how do we find the time? The easiest way to find the time is using the y direction to see how long it took to go up and then come back down. We can't really use any of the variables in the x direction to do that. So let's find the amount of time it took for the ball to go up and down in the air, right? So how am I going to do that? Well, I'm going to dang. Okay, so yeah, that's weird. So so good. Yeah. Okay, so I'm going to use this equation. So delta x equals velocity initial times time plus 1/2 acceleration times time squared. Okay, and all I'm going to do is I'm going to say, I'm just going to look at how long it takes to drop the ball from 60 meters, and I'm going to multiply that by 2 because essentially that's just going to tell me how long it took for it to go up and then how long it took to go down, right? Because it takes the same amount of time for the ball to go up in the air as it does to go down. So if I measure from, I can either measure it going up, right? I could do that if I wanted to, even especially because I have the velocity initial in the y direction now. I can measure that and then I can just multiply it by 2, or I can measure it from top going down and multiply that by 2, and that'll give me the time also. So let's just measure it from the top. So our displacement is going to be negative 60 because we're dropping the ball. Our displacement is negative 60 meters, and then our initial velocity is 0, right? Because it's starting at the top, 0. So time, the time variable goes away there, right? So whatever, time plus 1/2 times, again, negative 9.8 meters per second, and then times time squared. Okay, so it's perfect. That 0 cancels out that other time, so we don't have 2 unknowns. All right, so then when we solve this, the time is going to be 3.5. Okay, so we have 3.5 seconds. That's how long it takes to drop the ball, so going one way. So we have to multiply this by 2 because we want to see how long it takes for the ball to go up and down, right? This whole process, how long does it take this whole process to happen? And that equals 7 seconds. Okay, so it takes 7 seconds for this whole process to happen, right? So when I throw the ball, it takes 7 seconds for it to go 80 meters and hit the floor, essentially. Okay, now that we have time, we can plug that in and find the velocity in the x direction. Now let's use all of our variables in the x direction. So we're going to use this equation, delta x equals v0 times time plus 1/2 times acceleration t squared, right? So we have time now. We know delta x, it goes 80 meters, right? So the final is 80, initial is 0. We do not know. We're trying to find the initial velocity. Okay, we know that it takes 7 seconds to do this whole thing. The acceleration is 0. Okay, so this is 7. Parentheses. So this whole thing is going to be 0, right? Because 0 times anything is 0. And then when we solve it out, velocity initial, so you divide by 7, we get 71.58 meters per second. Okay, so now we have our velocity in x, which is what? It's not 71. No, I skipped ahead. Okay. So our velocity in the x direction is, sorry, my notes are scrambled. It's 11.42 meters per second. So if you solve it out, you get that. Okay. So then our velocity in the x direction is 11.42 meters per second. Okay. Cool. Now we have our two variables. So we have our x and our y, and then now we can get our we can get two things. We can get the angle, all right, and we can get the velocity, right? Cool. All right, so let's find that angle. I just realized I didn't solve for the diagonal velocity in my notes, so I had to pause to do that. Okay, so let's find the angle, right? So the angle at which it goes, yeah, so let's write this out. So we got, if I were just to blow up that segment right there, I got the ball going up, right? That's the initial velocity in the diagonal direction. We've broken it down into the x and y directions, right? So it goes 11.42 meters per second in the x direction, and it goes 34.29 meters per second in the y direction. Okay, so now to find the angle, what could we do? Well, if we use tan, all right, we can do tan of this. Tan angle equals, and then we just put 34.29 all over 11.42. And then when you solve for theta, theta equals, boom, that number I gave away earlier, 71.58 degrees. Okay, cool, so that's the angle. Good, it's one of the answers. Now we've got to find what the velocity is here. Okay, so we could just straight up use Pythagorean's theorem, a squared plus b squared equals c squared. So a squared is 11.42 squared plus 34.29 squared equals c squared. And then when you solve for c, you get, what do you get? 36.14 meters per second. Should be around that. Okay, cool. So that's number 3. Sorry, that took a while to. Okay, so number 4. In which case is the object's velocity changing while its speed is not changing? Okay, so what's the difference between velocity and speed? Velocity is a vector, right? And it's also has scalar quantity to it. So velocity is a vector, so it shows direction. Speed is just the quantity, it's just a scalar. Okay, so essentially, that's the only difference is velocity shows direction. So let's look at A. Is velocity changing while speed is staying constant? Let's see. So velocity is going, and we have velocity going in the horizontal direction, and then we have acceleration that is going sort of diagonal direction, but with velocity, right? Because it has some x component to in the same direction as velocity. So since we have some acceleration that is going with velocity, the speed is going to be increasing, right? Because remember in class when we said when acceleration is going in the same direction, so let's say acceleration is positive, velocity is also positive, so that just means they're in the same direction. Could be negative, you can switch the sign to be negative. It means we are speeding up. Okay, so in this case, it's speeding up, right? Because they're in the same direction. So our speed is changing. And if we were to say like acceleration is negative, velocity is positive, or vice versa, then we would see a slowing down. Okay. So let's look at B. So velocity is diagonal, and then acceleration is going straight up. So it looks like in this case, acceleration or velocity, if you break it down into its components, It's got some x, right, and some y. Okay, so it looks like the velocity in the y direction is going to be in the opposite direction as acceleration. So it's going to be slowing down. So our speed is going to be changing in this specific one, right? So that's not right. Let's look at C. Well, acceleration and velocity are pointing in the same direction. So we know our speed is going to also be changing. It's going to be speeding up, right? Same direction. Let's look at D. Okay, it looks like velocity is just straight up in the horizontal. Acceleration is in the vertical. So there's no y component to velocity. There's no x component to acceleration. So what do we think about that? It looks like, let's say the velocity is going in the positive direction here. Acceleration isn't going in the positive or the negative direction. So what does that tell me, like, about the speed, right? When we break it down into its x component here, because we only have velocity in the x component, it's telling me, let's say this is like ambiguous, or it's not ambiguous. It's essentially our car or whatever the object is neither slowing down or speeding up, right? Okay, so that's good. That's what we're looking for, right? Our speed is not changing, but is our velocity changing? Yeah, our velocity is changing. Why do I know that our velocity is changing here? Because I know that acceleration is just the change in velocity. That's all it measures, right? It's the rate of change of velocity. So we have an acceleration that's perpendicular to velocity. You know, I don't know, it kind of looks weird, but when you think about circular motion, right? So if we have something like a circle, this is the center of the circle, and then we have a velocity right here, tangent line, so the instantaneous velocity, okay? And then let's say our velocity changes, right? When we go in a circle, it changes. Okay, so if we were to take these two and measure their change, what is the change between that one and this one? That would be this variable right here, right? So this is a change in velocity, is this line, okay? What is that line? If I were to draw it, it would be pointing straight in, right, on each of these points. So the change from this to that line, this velocity to that velocity, we're going to have the acceleration that is pointing diagonally in towards the center. That's essentially what the acceleration is, right? It's a change in velocity. And in this case, it's going to be pointing in towards the center of the circle. Yeah. All right. So number 5, a moon revolves around planet X 5 times every 2 seconds. What is the frequency at which the moon revolves around planet X? And what is the period? Okay, so this is just definition of what frequency is versus what the period is. Okay, so what is a frequency? So a frequency is just a measure that gives the amount of revolutions an object or something is around another object per unit time, so per second, right? So how many revolutions can it do per second? Period is just how many seconds, right? So how many seconds it takes to do one revolution. So you see their units are sort of inverse. So frequency here, if we see that the moon revolves around planet X 5 times, there's 5 revolutions. So 5 revolutions every 2 seconds. When we simplify this, it'll give us 2.5 revolutions per second, okay? So how do we get period here? Okay, how do we get period? So period is just how many seconds it takes to do one revolution. So if we just flip these, right, period is, it takes 2 seconds to do 5 revolutions, then we get a period of 0.4 seconds. Okay, so you see that we see that sort of period and frequency are inversely related. So you can derive this equation where period is equal to 1 over frequency. Okay, but they are different. They're different things that you're measuring. They're different variables when you talk about them. Okay, so just keep that in mind. All right, so number 6, we got a ball is attached to a 1.5 meter string that moves in a vertical circle. Okay, what is the minimum speed that the ball must have at the top so that it continues to move in a circle? Assume the acceleration of the ball at this point is 9.8 meters per second squared. Okay, so we got a ball attached to a string, it's going in a circle, and it's at the top right now, right? So we got this ball. It's at the top, it's moving in this circular pathway around this point. Okay, so what do we know at this point? We know that the string is 1.5 meters long. We know the acceleration, which is pointing inwards, is 9.8 meters per second. We want to find the velocity. Okay, we want to find out which velocity, what velocity do we need with the minimum speed that we need to keep that ball in a circular motion. Okay, so I didn't even really need to give you the acceleration right here because you could assume that acceleration is sort of like due to gravity here, which is 9.8, right? So when we do this, we have this equation, acceleration equals velocity squared over r, and we can use this equation to find our velocity measured. Okay, so acceleration here is 9.8 equals velocity squared over 1.5, right? When we solve it, velocity was gonna equal 3.8 meters per second. Okay, so it takes the velocity of this ball has to be at 3.8 meters per second for it to continuously go in a circle around that dot. If it's anything lower than that, then the string, essentially, it's just going to go inwards, right? It's going to fall to Earth, right? That's why we know that the gravity is negative or 9.8 meters per second at that point. And that influences sort of the change in the velocity, right? So if the velocity were to decrease, that would be a big part of it. All right, so yeah, if you guys have any questions, go ahead and comment on this, on the video, or you can come to my office hours and ask me questions about it, and I will answer them to the best of my ability. Please do sign in. I'm going to post a sort of sign-in link at the bottom. If you've watched the video, please go into the description of the video and sign in just to show that you did watch the video, and it helps me out, helps attendance, and it's kind of hard getting attendance right now for the SI. So if you do that, that'd be awesome. All right, hope you guys have a good week.